Hello everyone. Today we will discuss the differential privacy algorithms for machine learning. This is a continuation of the previous lecture where Francisca covered the introduction to privacy and talked about the privacy leakage, inversion attacks, membership inference attacks, and gave you an intro to differential privacy. Before we delve into how to prevent the privacy leakage from ML models, let us first recap the intuition behind differential privacy. To implement formal privacy guarantees, we use the mathematical framework of differential privacy, in short DP. Differential privacy defines what it means for an algorithm to be private. The idea is that a randomized algorithm, also called mechanism M, should produce indistinguishable outputs on two versions of dataset, D and D prime. The first version data, D, contains a record corresponding to an individual person, and the other version, D prime, does not contain this record. If these outputs from the algorithm or mechanism M, based on data D and D prime, are indistinguishable, then an adversary who is observing the outputs is unable to determine if we operate on the first, D, or the second version of the dataset, D prime. As a consequence, the adversary does not know if this individual contributed his or her data record or not. So if the answers were always indistinguishable, then the algorithm would not be useful. Thus, instead, we have probabilistic guarantee, and now let us unpack this inequality at the bottom of the slide. So the main inequality to define differential privacy is expressing this intuition that model produces indistinguishable outputs on any pair of training dataset D and D prime that differ only by a single data point. So here the main inequality first has this element upper M, standing for an algorithm or a mechanism. It represents a randomized mechanism or algorithm in the context of privacy for machine learning models. M denotes the training mechanism. S is the set of possible outputs, in this case the model weights or outputs from the model. Epsilon is the most important parameter in DP. The smaller the epsilon value, the stronger privacy guarantees. So epsilon defines how close the model's weights or predictions should be. This implies that an adversary observing the outputs of the training algorithm, for example, the model parameters or its predictions, can improve its guess at most by a bounded probability, in this case defined by epsilon, when inferring properties of the training data that were used to create the given model. And we also have this additional parameter called delta, which stands for probability of failure. So without the delta, this is the pure differential privacy, and with the delta is so-called approximate differential privacy. And this DP version with delta is the most widespread relaxation of pure epsilon differential privacy. So epsilon delta differential privacy weakens the definition by allowing an additional small parameter delta, which is the density of probability, on which the upper bound epsilon does not hold. So here the parameter delta can be thought about as a probability of a failure. It is a similar concept to one in cryptography, where there is some small probability that an adversary can guess our private key. Now, what is the intuition behind the privacy for machine learning models? We start from a simple baseline. If your ML model has never seen your data, it cannot possibly violate your privacy. This obtains perfect privacy with epsilon equals 0. What is the privacy concern if your private data is added to the training set of the ML model and the model changed significantly compared to the simple baseline, so the model trained without your private data? You can be concerned about your privacy in this case. So how to measure the privacy leakage? We cannot simply measure how different the weights are between two different models to measure privacy leakage, because any change to the training process of the model will potentially significantly change its parameters. Permuting the training data randomizing initial parameters or running another task on the same GPU will produce a different model with potentially very different weights. So if we expect that addition of private data would not change the model at all, then the data used for training would be useless. So the differential privacy framework solves these two problems pointed out in the previous slide and enables us to measure the privacy leakage from ML models. So first, rather than comparing the weights of the two models, we want to consider the probabilities of observing these weights of the models. And then, instead of insisting that nothing will change, let's instead promise that while something will change, we guarantee it will never change by more than a specific and predefined amount. This way, the observer of the model weights won't learn too much about our private data used to train the model. But we can still learn enough from the private data to produce useful models. So these two principles are embodied in the definition of differential privacy. What does it mean intuitively is that if after training two models, one of which on all data, mine included, and the other on all data except my data points, you can prove that all weights of the two models are observed with probabilities that lie within a predefined boundary of epsilon to exponent to the epsilon of each other. Then we can claim that we have provided the epsilon DP guarantee for our training procedure. The differential privacy framework requires us to design two aspects. So the first aspect is a mechanism, which is the algorithm that expresses how should we train a model so that we can preserve the privacy of the training data. So we have to ensure that the impact of individual data on the outputs of the model, or outputs of the mechanism in this case, so the model parameters, is limited. And second aspect that we have to guarantee is that it cannot be easily distinguished from the impact incurred by other data points. So if we train our model on a given set of data points versus other that we've changed only of a single data point, then these outputs from the mechanism, meaning in this case the produced models, model weights, should be roughly the same. And this preview is of a snippet of code which shows the gradient clipping and noise addition. And these two lines of code, they express how we can realize these two goals. And very soon we'll see how we can integrate these two aspects into the training algorithm for an ML model. So in general, the basic blueprint, so the schema for designing a differentially private additive noise mechanism is to approximate the functionality by sequential composition of bounded sensitive functions. Here we bound sensitivity by clipping the gradient. This is in the preview code, the line A. And then we have to also choose parameters of the additive noise. So how much noise we add, in this case, how much of the Gaussian noise is added to the clipped gradient. And after we design the mechanism, the second step is to also account, so to calculate how much privacy loss was incurred from the, in this case, given model based on the private training data. So the accounting just analyzes privacy costs, privacy leakage from the training mechanisms, and it is in most cases, we will see that today, is quite a difficult aspect, and then it requires very rigorous mathematical analysis. So let's start from the beginning. So we start from the standard training of ML models, where we have some private training data. In this case, training data from users Alice and Bob. And we want to protect this data, but at the same time, we'd like to leverage the data to train the model. So the DP algorithms for ML were designed with the consideration for strong adversaries that have some additional capabilities. So this is expressed in the way that the adversary is, let's say in this case, like the one from MIA attack, which was described in the last lecture. So this is membership inference attack. And then here adversary has a full access to the model, so for example the model parameters, and can even see the gradients used to update the model parameters. The approaches that leverage DP for machine learning offer protection against such strong adversaries. So this protection is attractive in particular for applications of machine learning on mobile phones, tablets, and other devices. So storing models on device enables power efficient, low latency inference and may contribute to privacy, since inference does not require communicating user data to a central server. On the other hand, we must assume that the model parameters that are stored on these mobile devices may be exposed to hostile inspection. So in this case, this adversary might try to analyze the model outputs and based on them infer which of these training data points were used or not for this given model. An adversary, apart from having access to the model outputs, can also analyze model parameters and potentially even updates that were produced during training of the model. So, differential privacy has several properties. We'll touch here upon 4 that make it particularly useful in applications of ML that have to protect privacy. And the first property is composability, which enables modular design of mechanisms. So if all the components of a mechanism are differentially private, then so is their composition. And in last lecture, we also discussed simple composition, where we, for example, have two mechanisms, M1 and M2, and then we can just easily combine them by computing the privacy leakage as being epsilon1 plus epsilon2 incurred from these two mechanisms separately. And example of this property is in the training of ML models, where we apply DP mechanism to each step of the training when we change the model parameters according to the computed gradient. So in the training of the model, we might have many iterations, and we compute the privacy leakage per iteration, and ultimately, thanks to this property of composability, we are able to compute what is the privacy leakage after the whole training of the model. What are other properties that are useful when training ML models? One of them, for example, is group privacy, which implies that we have this graceful degradation of privacy guarantees if data sets contain correlated inputs, such as the ones contributed by the same individual. So it might happen that we don't have this perfect data set, so some of these data points correlate, or maybe we have repetitions of data for a single user, and then despite that problem, DP still is able to gracefully degrade the privacy guarantees. And then how do we do that? So here we define a mechanism that for a given data set produces output, in this case some models, and we want this mechanism to be epsilon data differentially private. But if in our data set, in this case data set D and D prime, there are k positions on which data set differ, so not only one difference between the data sets, but more than one, then this epsilon value is just multiplied by k. So this is how we can gracefully degrade the guarantees of our algorithm. And then another aspect is robustness. So this property guarantees that even if adversary has some auxiliary information about the model or potentially even data set, then this privacy guarantee that we compute with DP still holds and is not affected by side information available to the adversary. And one of the important other properties is post-processing, which means that it is always safe to perform arbitrary computations on the outputs of a differentially private mechanism. Okay, so let's start from the beginning of the training of ML models. So here we present the standard SGD algorithm. So SGD stands for stochastic gradient descent. So in this algorithm, at each step, one forms a mini batch of random examples. In this case, we just limit this to just a single random example, x sub I, to simplify the presentation. And to start from the beginning, we have as input model with parameters theta. We define some empirical loss function here, L, and we said we have some data points for training from x1 to x sub upper n. And also during learning, we use some learning rate, in this case being eta. So we consider upper T training rounds. We start from selecting a random data point, x sub I, and then compute a gradient for this data point. So taking into account current model parameters, theta sub T, and then for this training round, and this given data point, we compute loss, which can be, for example, a standard cross entropy loss. And thanks to that, we get a gradient for model parameters. And then once we compute the gradient, we finally take a step in the opposite direction to the gradient. So we want to navigate our model parameters to get to the local minimum for our loss function. So this is standard algorithm, how you train the ML models without any privacy. And then how to make sure that our model after training preserves the privacy of the training data. So one might attempt to protect the privacy of training data by working only on the final parameters that result from the training process, and then treating this process as a black box. Unfortunately, in general, one may not have a useful tight characterization of the dependence of these parameters on the training data, adding, for example, overly conservative noise to the parameters, where the noise is selected according to the worst case analysis, and this actually would destroy the utility of the learned model. Therefore, a more sophisticated approach in which we control the influence of the training data during the training process is better, and in this case we apply this mechanism during the SGD computation, so for each step of the training of a given model. So now, to obtain a canonical version of how to train models with privacy, called DP-SGD, so this is just a SGD with differential privacy, we add only these two red lines. So we add these two additional privacy parameters to the standard ML. So we have some noise scale sigma, so how much noise we add to the gradients, and also we have to bound the norm of the gradient. So this will be explained here. So these two lines express first clipping of the gradient. So what we do is that we take the gradient computed in the previous line, and then we clip that gradient if its norm is above C, to be exactly C. If the norm is already below C, then we don't clip the gradient. And this clipping is to ensure that a given data point does not have too much impact on the model parameters. And then the second line is to add Gaussian noise, and this is to protect privacy. So the random noise added to gradients prevents the final model outcome from reflecting the gradients of any individual data point, and this protects privacy. So essentially, in the second line, we want to ensure that even after clipping the gradient, still we cannot, as for example adversary, find out that a given data point was used to train the model. So it further limits the impact of a given data point on the obtained model parameters. So let's maybe unpack more these two aspects. So the first one is about norm clipping. So proving the differential privacy guarantees requires bounding the influence of each example on the gradient G. So we clip the gradient so that we have a bounded sensitivity. So we bound how much influence a given data point has on the model parameters, and we clip each gradient in the L2 norm. So the gradient vector G is replaced by G over max of 1 and the norm of G times C for a clipping threshold C. So this clipping ensures that if norm of the gradient is greater than C, it is scaled down to be of norm C. So intuitively, the gradient should lie within this L2 ball of the radius C. So again, if our gradient G sub I is of a too high norm, so in this case this black arrow, then we just clip that to be within this L2 ball of radius c. If the gradient g sub j is within this L2 ball, then we simply don't clip that. And it's expressed also in these two equations below. The gradient clipping is a popular ingredient of SGD for deep networks for non-privacy reasons, especially to prevent the gradient explosion, which halts the training process. Though in that setting it usually suffices to clip after averaging the gradients from each point in the mini-batch, whereas in DP-SGD algorithm we clip the gradient for each individual data point. So to make it clear, in the standard algorithm we take a so-called lot of examples L sub I instead of a single example X sub I in DP-SGD. And then we compute the gradient for each example separately and then clip the individual gradients. The noise is added to the accumulated clipped gradients. DP-SGD uses Poisson sampling, where every example X sub I is selected with probability Q equals L over N, where L is the size of the lot and N is the number of data points in the training set. So again, the lot is just sampled data points from our training set that we would like to use for a given training iteration. The expected size of this lot L is here also upper L, since we sample from n private training data points, so x sub 1 to x sub n in each iteration. And then in expectation, this is the size of the lot. However, in practice, if we just use the DP-SGD algorithm to train our model, then for a given iteration, if we check how many data points are already selected for the given iteration, there can be, for example, smaller than a number of expected data points L or larger. And then on average, if we just calculate how many data points were used per iteration, it is indeed, as expected, the upper L. And now, why do we do that? Why do we use this Poisson sampling mechanism during training of our models with DP-SGD? So this Poisson sampling leverages the so-called privacy amplification by subsampling principle. And this is a very popular principle in DP literature, where we ensure that differentially private mechanism run on a random subsample of a population provides higher guarantees than when we run on the entire population. So this algorithm essentially takes into account that for a given iteration of DP-SGD, we don't use the whole training set of size n, but we just use this smaller subset of the training set called lot, and then we take into account this in the privacy analysis of our algorithm. So how now we go from this simple composition that we described in the previous slide to the advanced composition? And why do we talk about that? So first of all, we care about that because we have to use this composition of many mechanisms during the privacy accounting for machine learning algorithms. So composability property is used for, in this case, privacy accounting for ML, and then in this case for the SGD algorithm. And the composability of DP allows us to implement the accountant procedure that computes the privacy cost at each access to training data and accumulates this cost as the training progresses. So each step of training typically requires gradient at multiple layers, and the accountant accumulates the cost that corresponds to all of them. So in the previous lecture, we discussed the simple sequential composition. So this says that if we have two sequential mechanisms, m sub 1 and m sub 2, then we can combine them, and the respective epsilon and delta values have to be simply added up. So the extension is the basic composition, where we have t such mechanisms, so m sub I, and each of them is with the epsilon sub I, delta sub I DP guarantees. So the mechanisms are chosen here sequentially and adaptively, which means that the next mechanism can be based or depends on the previous mechanism selected for example, in the training process. And then the final mechanism that we obtain after sequentially adding these mechanisms is with sum of these epsilon values, sum of these delta values from each of these m, for each of these mechanisms m. So important note here is that all of these epsilon values from all of these mechanisms are of the same value, epsilon and delta, and then in the simplified version, this t applications of mechanism m amounts to t times epsilon and t times delta dp guarantees. And the basic composition is already a powerful result, despite actually its simple proof. It establishes the fact that dp is so versatile and allows us to begin reasoning about complex systems. So in terms of like how we can construct the building blocks to construct complex mechanisms. And one of these complex mechanisms actually is training of the machine learning models. So once we establish that, now we can move on to the very important result, which is called advanced composition. So advanced composition states that if we have these parameters epsilon, delta, and delta prime, and we have again this sequence of mechanisms m, so we have mechanisms m sub 1 to m sub upper t, so we have t such mechanisms, so we can think about that as being t training rounds of the ML model, and they are basically sequences of epsilon delta dp algorithms. So every of these upper m's is algorithm with epsilon delta guarantees, and again we choose these mechanisms in a sequential way, also adaptively. We can choose the next one based on the previous one. Then the final mechanism that we obtain, so in this case training of the ML model, is epsilon tilde delta tilde dp. And here we have a bit better guarantees. Actually, in the case of many training rounds t, these are much better guarantees than the guarantees from the basic composition. So here, this epsilon tilde amounts to this quite complex expression. However, it can be estimated roughly to be square root of t times epsilon. So this is saving the factor of square root of t compared to the basic composition in terms of the final epsilon value. And also for delta tilde, we also have we also have similar in this case guarantees as for the basic composition. However, the main aspect is really to lower the cost of the privacy through this parameter epsilon. And here we basically assume that this delta prime, which is a slack parameter added to compute this epsilon tilde and delta tilde, that this actually delta prime parameter is roughly equal to delta, which is usually a very small value. So when you train ML models, usually you set this parameter delta to be equal 1 over the number of data points in the training set. So let's say if you train model on MNIST dataset, which contains 60,000 examples, then your parameter delta for training this model with privacy would be 1 over 60,000. So we have 3 mechanisms used during the training of ML model. The first mechanism is the Gaussian mechanism, where we add the Gaussian noise to the clip gradients. And remember that we clip the gradient to limit the sensitivity, so limit impact of a single example on the trained model parameters. The second aspect is the privacy amplification by subsampling, where for a given iteration we do not use the whole training set, but we Poisson subsample the from training data to create a lot, so some subset of the training data. And finally, we use the advanced composition to add up the privacy budget epsilon incurred in every iteration. So the initial composition of these 3 components provided us with the given estimation of the privacy loss. Here the epsilon value is multiplied by the Q, which is the probability of selecting a given training example for a lot, and then also by this square root of t times log of 1 over delta. So this is a multiplier incurred from many iterations of the training algorithm. The delta is assumed to be t sub t times delta, since we assume that t is much higher than q. So this is roughly amounting to t sub delta. And then what was really important was that the paper, which actually proposed the DP-SGD algorithm, leveraged something which is called moments accountant, which we will explain very soon, to limit how much privacy is incurred from our private training data while computing the model parameters. So the paper on the DP-SGD showed that the privacy loss can be further reduced to only big O notation. So this is just an estimation that this epsilon value would be roughly Q, so this subsampling ratio, times epsilon times square root of t, and delta dp. So the main point is that the log of 1 over delta multiplier was removed from the epsilon, and the factor tq was removed from delta. So this is a very important result that shows that in principle, if we train ML model, then defining delta, as we discussed, 1 over number of training data points, and then incurred epsilon value is just epsilon for a single training iteration times square root of number of training iterations and the ratio of sampling a given data point from the training set. So let's discuss more how this result can be obtained. So before we delve into these details, we have to first analyze if this is useful. So here we show that we showed what is the difference in the privacy guarantees in practice between advanced composition and moments accountant. And actually this difference between these two ways how to aggregate epsilon values is really significant. So here in this graph, the y-axis represents the epsilon value with, and the x-axis is the number of training epochs for an ML model. So this figure shows two curves corresponding to advanced composition, so this curve with the empty squares, and the bottom line is for the moments accountant. So we can see that we get a much tighter estimation of the privacy loss by using the moments accountant than by using advanced composition. So for example, when we train the model, and in this case under this advanced composition for 100 epochs, the value for this epsilon is only 1.26, whereas for the standard advanced composition it's approaching 10. If number of epochs is increased to 400, this value for moments accountant is only roughly 5 probably, whereas for the advanced composition it's approaching 25. So this shows that the moments bound they achieve much tighter privacy guarantees than the one via advanced composition. So the latest work also audits the DP-SGD and shows that this privacy analysis through moments accountant is not far from the optimal one. So to explain moments accountant for accounting privacy leakage during training of ML models, we have to introduce a few additional concepts. So here let's go back to the initial definition of DP. So initial definition considers that we have S, upper S, which is set of outputs. And then, just for simplification, here we consider that instead of having this set S, we have some output value lower z. So we call it z here. So this is single output from a mechanism. In this case, we can think about that as single model parameters after training of the ML model. So, taking into account this inequality, we can simply divide the left side by this expression probability of m of d prime equals z, and then this whole expression, the ratio of probabilities, has to be less than or equal e to the power of epsilon. Next, for both sides, we take the logarithm, and we have now the logarithm of the ratio of probabilities being less than equal epsilon. And now we can define the privacy random variable, which we call L, of sub of m sub d and m sub d prime. So this privacy random variable L is defined as logarithm of this ratio of probabilities for m of d equals z over probability of m of d prime equals z. So let us analyze more the privacy random variable L. So in this case, for pure DP without any delta, so this is in the green color, the variable is less than or equal epsilon always, and its probability 1. Whereas in the blue color, the approximate epsilon delta dp, the privacy random variable L is less than or equal epsilon, but with probability 1 minus delta. Thus the guarantee might fail with probability delta. And when we visualize the probability distribution of the privacy random variable L, the x-axis represents the value of the privacy loss random variable, while the y-axis is the probability distribution. So in the graph, the green line represents the pure dp, while the blue line represents the approximate epsilon delta dp. The blue area on the left from minus epsilon and to the right from plus epsilon should be equal to delta. But the mass of the probability can be somewhere out there. So, for example, in this case, we show this probability delta being here. So, quite far on the left-hand side. Interesting aspect is that the epsilon delta dp, the approximate version of dp, does not allow us to distinguish between this blue and then this red curve. So, the next concept that we will discuss tries to better define the privacy loss random variable. So it does not try to control only the mass of the privacy random variable, but also controls the moments of the privacy loss random variable. So the other approach to control this privacy loss random variable is based on moments accountant. So again, it tries to control not how much mass of the privacy random variable is outside of the interval from minus epsilon to plus epsilon, but it expresses that through the moments of the privacy loss random variable. So why do we want to use moments here? So intuitively, moments of a function are quantitative measures related to the shape of the function's graph. If the function is a probability distribution, then the first moment is the expected value, the second is the central moment, it's also called variance, and the first standard moment is the skewness, which measures the asymmetry of the probability distribution, and we have more moments like that. So the approach to think of a random variable in terms of moments relies on the fact that for a distribution of mass or probability on a bounded interval, the collection of all these moments of orders from 0 to infinity uniquely determines the distribution. So this is the main point to remember about the moments as another way how to express the shape of the function. So we here define a new inequality. So this is this new version of how we can control the ratio of the probabilities between the mechanism on dataset D versus D prime. So in the previous version, we want the random variable to be less than e to the power of epsilon. Instead now, for this new inequality, we want to control the expectation of the random variable. So we want to make sure that the random variable raised to some power lambda is less than some value gamma. So this gives an intuition of how large the random variable can possibly be. It also gives the distinction between the orange and the blue curves. So how to intuitively think about that is that here we don't specify a given value through this ratio, but we want to do that through the expectation of these ratios. So how to compute the delta for such a defined random variable? So we take from the previous slide this way how to define the privacy random variable through the expectation, and then with the power to some power delta, some power lambda less than or equals specific value gamma. So we operate with this expression. So our goal here is to find out if for such specific expression of privacy laws, how can we compute parameter delta. So this is our goal to achieve here. So we have to change this inequality, and then let's go through this step by step. So here what we do at the beginning is that we exponentiate both left and the right sides of this inequality. So we get just expectation on the left hand side and the exponent of the gamma on the right hand side. And then the delta is defined in the standard scenario as the probability that this privacy random variable is greater than or equal epsilon. So this is actually failure of the guarantees. And then here we want to multiply both sides of this last expression by lambda and take the exponent. So this is what we get after this transformation. So here is the delta from the previous slide, and then in the next step we just remove this exponent and logarithm, so they cancel out. So we just have delta as being probability of these ratios of the probabilities to the power of gamma, which is greater than or equal exponent of gamma times epsilon. And for the next step, we use Markov's inequality. So if x is a non-negative random variable and alpha is a constant greater than 0, then probability that x is at least a is at most the expectation of x divided by a. So this actually is a standard Markov inequality. And we just leverage this inequality for this last expression. So we can now bound the delta as being less than equal of this expectation. So our upper x here is this part with the ratio of probabilities to the power of lambda. So we take expectation of this value, and we divide by the parameter alpha, in this case being this exponent of lambda times epsilon. And then we can further simplify this expression by using the value from the previous slide. So this expectation of this ratio of probabilities to the power of lambda is less than equal exponent of gamma. So this is how we can simplify from this expression to these ratios of exponents, and then finally we can just simplify that as being lambda minus gamma minus lambda times epsilon. So The main goal of this derivation was to first that we want to define in a different way the privacy accounting, and we assume that we have the following. So we assume that we have the following random variable, and then once we define this random variable this way, then we can then this actually implies that we can for the given parameters gamma and lambda, we can select some epsilon, and then by selecting some epsilon we can compute the corresponding delta. So the main point is that by bounding the random variable in this way, so this expectation of the ratios of the probabilities to the power of lambda, by bounding by some value gamma, we can infer the corresponding epsilon delta DP guarantees. So initially, moments accountant was used in the paper on DP-SGD for tracking privacy loss across multiple invocations of the Gaussian mechanism applied to random subset of the input dataset. And then, how can we further extend the moments accountant? So moments accountant also have other further extension to relax the standard DP, and it pointed out to adopting so-called Renyi differential privacy as an effective and flexible mechanism for capturing privacy guarantees of a wide variety of algorithms and their different combinations. So first we have to define Renyi divergence. So this is a similar definition to that of the privacy loss random variable. So in this case all algorithms are natural, and in this case this P of x is the density of P at x. So just going back to the initial setup, so we define this new way how to think about privacy random variable, and extension to this moments accountant was proposed to leverage the Renyi divergence. So this is standard definition of Renyi divergence, where we just have this factor 1 over gamma minus 1 multiplied by the logarithm of exponent. We then draw x from the probability distribution upper p, and we have this ratio of probabilities p of x over q of x to the power of lambda minus 1. So the point here is that this expression for the Renyi divergence really resembles closely this privacy random variable that actually was defined for the moments accountant. Let us take the definition of Renyi divergence from the previous slide, and based on the Renyi divergence, another relaxation of DP was defined. This relaxation is called Renyi DP, or in short RDP. The definition of RDP closely resembles the standard definition of DP. A randomized mechanism M is said to have epsilon Renyi differential privacy of order lambda, or lambda epsilon RDP for short, if for any adjacent datasets D and D prime, the inequality at the bottom of the slide holds. Let us interpret the inequality. The mechanism M is said to be epsilon Renyi differentially private for order lambda. Again, here, the privacy loss random variable takes the expectation of the ratio of probabilities raised to the power of lambda minus 1 instead of using directly the ratio of probabilities as in the standard definition of differential privacy. RDP inherits many properties of standard differential privacy. You can easily go back from RDP to the standard epsilon delta DP. Similarly to standard DP, Renyi DP also provides the group privacy to gracefully degrade the privacy guarantees if dataset contains correlated inputs. It is also robust to auxiliary information. So again, we have no assumption on the adversary's knowledge. RDP also provides post-processing guarantee, thus it is safe to compute on outputs from RDP mechanisms without any further loss of privacy. Finally, RDP also provides sequential composition and can be used to construct complex mechanisms composed of many simple mechanisms. It is especially useful for the ML privacy for DP-SGD as well as for the next framework that we will discuss called PATE. Another canonical approach to achieve privacy for machine learning is by the PATE framework. So PATE stands for Private Aggregation of Teacher Ensembles. In PATE, instead of training a single model on a dataset, we partition data into n subsets. And these subsets are in the mathematical sense, thus they do not overlap. Then we train a machine learning model called a teacher on each partition, and we do it independently for each partition. So after this step, we obtain n teacher models. Next, when a new query comes, we run inference on each teacher and aggregate the predictions from these teachers. We use a public set of data and label them using the noisy aggregator. Finally, we train a model which is called student on this noisily labeled public data. So this is where the transfer of knowledge happens from the teachers to the student model, and this is done in a differentially private manner. The privacy mechanism for PATE is based on the noisy aggregation. Let us assume that the teachers vote if a given movie review is positive or negative. Thus, we have a standard classification with two classes. Each teacher returns a vote which is either positive or negative. Then we aggregate these votes into histogram, and then here we see that more teachers voted that the movie review was positive than the movie review was negative. And on top of these histograms, we add Gaussian noise. So actually this is how we realize differential privacy mechanisms for the PATE framework. So we add this Gaussian noise on top of the histogram, on top of these vote counts. This is the privacy mechanism for PATE, and then after this step, we take the noisy argmax of the histogram counts and return the label with the highest noisy count, which in this case is the label for the class positive. Let us define this mechanism for PATE a bit more formally. So we want to define this Gaussian noisy max aggregation, in short called GNmax. So here assume that we have a sample X. This sample comes from the public dataset, so it's not private, and we want to label this given example. We assume that the task has classes from 1 to m, and then we denote by f sub j of x the output from a given teacher, from teacher j in this case, and the teacher just outputs one of the classes from 1 to n. And then we also have to define this n sub I of x, which is number of votes for the ith class. So here we have just count of teachers j that returned this class I. So again, n sub I of x defines how many teachers voted for class I. Having said that, we can now define this mechanism. So mechanism denoted as upper M of sub sigma. So this is sigma that denotes variance, sigma squared, in the Gaussian noise. So the mechanism itself just defines formally what we saw in the previous slide. So here we have number of votes for each class I, and to these vote counts in the histogram we add Gaussian noise with mean 0 and sigma squared variance. After adding this noise on top of the histogram, we take the argmax, so we return the class that has the highest value after adding this Gaussian noise. So in principle, what we really want is that we want to, of course, return the class that receives the most votes from the teachers. However, because of the noise addition, it might happen that the class which was not selected by teachers as the class with the highest number of votes is returned from the mechanism. So in some cases, adding this noise can make the prediction actually incorrect, meaning not as indicated by the teachers. We can further improve this mechanism for PATE, And then intuitively, what's really happening is that when there is a strong consensus among teachers, the label they most agree on does not depend on the model learned by any given teacher. So this collective decision is intuitively private with respect to any given training point, because such a point could have been included only in one of the teacher's training set. So it means that if many teachers agree for a single class as being the correct one, then the mechanism should not incur that much privacy leakage. However, if we observe that teachers actually do not agree fully, there is no strong consensus, then in such cases the privacy leakage might be large, because a single teacher, for example using a single data point, could change the final prediction from the ML model, in this case from the ensemble of teachers. So the way to achieve the goal of a better mechanism is to filter out queries for which teachers do not have a sufficiently strong consensus. So this filtering enables the teachers to avoid answering expensive queries in terms of the privacy cost. So how do we really improve this mechanism? So this is called confident version of GNMax, and the algorithm is as follows. Given a query data point X, consensus among teachers is first estimated in a privacy-preserving manner, and then only we reveal the confident teacher predictions. So how does it work? Let us now provide the final algorithm itself. So we have some input, data point X. This is this public data that we want to label. We have some new parameter, which is threshold upper T, and additional parameters sigma 1, sigma 2 for the noising. And then to define this confidence for teachers, for their consensus, we have this additional check. So what does it mean? So here we take the values of the counts for each class, and we add first some other version of Gaussian noise compared to the mechanism defined in the previous slide. And then once we have this new noisy histogram, we check what is the max value for a given class. So so we actually find the value after adding the noise of the vote count, that is a maximum value, and compare that with this threshold T. And if this value is above the threshold T, then we proceed as in standard noisy GNMax. However, if there is no enough consensus, then we abstain from answering a given query. So the important parameter here is this upper T, which really defines to what extent we want for the teachers to have consensus. And usually we set this parameter T to be relatively large. For example, if the noise value is, let's say, 40 for 150 teachers, then we set this parameter T to be, for example, 170, which means that in some cases you set this parameter to be a bit higher than number of teachers in the ensemble. So this expression can clearly pinpoint to what extent we want teachers to have consensus. And then note that we have these two values of sigma. So one of them is just to privately check for consensus. Other one is just to run the standard GNMax algorithm. So in this case, the teachers do have consensus. So in this case, we check that most of the teachers agree what is the correct class. Then we just again take this number of counts per class in the histogram. We add another version of the noise, then take the argmax, and so again we find the class with the highest number of votes, and then return the noisy argmax, so the class with the highest number of votes. So these two steps are separate. One of them is just to check for consensus. Another one is to privately release the label. And you have to here note that these are separate mechanisms. And then if this first if fails, then we don't answer the queries. However, important aspect here is that even if we don't answer the queries, we still pay a given query, we still pay some privacy cost for checking if there is consensus between teachers. If there is consensus, then actually we pay the privacy cost twice. Once to check if there is this consensus between teachers, and second time to privately release the label from teacher ensembles. Knowing that, let's now consider how to do privacy accounting for PATE. So, privacy accounting for PATE uses RDP, R&eDP. The main difference between DP-SGD and PATE is that in PATE we have data-dependent analysis of privacy. So, if we would take the code for the PATE framework, we would see that we iterate through all the queries that are answered by the teachers. So again, in PATE framework, we have this public data, and then teachers, in a private manner, label these data points in a noisy manner, and for each of these queries, we separately account what is the privacy leakage from the original training data, on which we train the teacher models. So for each query, we compute how much privacy this given query incurs from the private data. The main point for accounting for privacy leakage in PATE is to bound the probability Q tilde. This is the probability that incorrect class is returned from the histogram. So here we define this probability. So we say that mechanism, in this case this PATE mechanism, returns a different class than I star. And I star is defined as the class that teachers voted mostly for. So this is the class in the clean histogram without the noise that has the highest number of votes from teachers. And we want to bound the probability that this mechanism returns class which is different than this class that is max class from the teachers. So we have to consider this Q tilde probability bound, and in principle it is bounded, and then we might still not return this correct class I star because of the privacy noise that is added to the histogram. The question is how to bound the probability Q tilde. This I star defines the class with the true plurality, so that class for which teachers voted most. And then we consider this I star as being one of the classes from the M classes for a given task. And here is how we bound this probability. So the probability is bounded by using the ERFC, which stands for the complementary error function. And then let us interpret this inequality. So when the probability that the incorrect class is returned to be less than a specific value. So we consider two values, n sub I star and n sub I. N sub I star is number of votes for the class with highest number of votes from teachers, and n sub I is number of votes for any other class. So if we are in if the number of votes for the correct class, so in this case number of votes expressed by n sub I star, is much larger than number of votes for any other class, n sub I, then we are in the right hand side of this ERFC, complementary error function. So if you consider that we have n of n sub I star to be really large, for example 100, but n sub I is very low, let's say 0, and we are far to the right in this ERFC graph, and then we have value 0. So this probability would be bounded in this case just by 0, but you also have to take into account other classes. But in principle, if the number of votes for one of the classes, in this case I star, is much higher than for all other classes, then this bound is very tight. This is very, very small value that incorrect class is returned. And then for such cases, the privacy leakage is very low. And this probability actually is taken into the privacy accounting. However, if in the worst scenario, there is another class that has equal or higher vote count than the correct class, then the probability of the failure approaches 1. So how it works is, for example, if n sub I star is equal, let's say 100, but n sub I is equal 99, then basically this is 1. And then for 1, we still see here quite large probability of, like, let's say 0.2. If the number of votes for the correct and incorrect class, let's say, are equal, then this number actually would be 0, and then we have probability 1. So if the two vote counts for two different classes are the same, then this probability is just equal 1. And then we also incur very large privacy leakage. So in principle, what we want is that if the teachers have high consensus, so n sub I star is much larger than any other n sub I, then we want to return the answer. In the other case, because of the high privacy leakage, we just refrain from abstain from returning the answer. Let us now compare DP-SGD versus PATE. In terms of privacy concepts, DP-SGD adds noise to model parameters, while PATE adds noise to the votes from teachers. The main part of the privacy mechanism in DP-SGD is to clip gradients and add noise to the clipped gradients. On the other hand, in PATE, we train teacher models on the private data and add noise to the histogram and train student model from scratch on the noisily labeled public data. Then another aspect is that DP-SGD, in terms of privacy analysis accounting, is data independent. So depending on what kind of data we use to train the model, we have the same privacy accounting. However, in PATE, we have data dependent privacy analysis, which means that our final epsilon value depends on what kind of queries we used, for example, in this public set in PATE. What are the requirements? In terms of the requirements, we can integrate DP-SGD into standard training of any model, and in most cases we now have methods to do that. There are some exceptions. For example, we have to cater for specific layers and adjust them to be differentially private, but in most cases DP-SGD can be out of the box applied to training of a given model, especially with these libraries like Opacus. And on the other hand, PATE has some requirements. For example, we have to have access to some public data to train the model which is called student. And now in terms of the applications, I will explain more and give some concrete examples of how can we use DP-SGD and PATE, and we do that, for example, for the large language models. So now let me show you examples of DP-SGD and PATE for LLMs, for large language models. This is an additional material for those of you who are interested in these topics and would like to delve deeper into them. First, we have to define what is a soft prompt. So here we assume that this is some large language model, and then this language model receives some input text. In this case, for example, we want to have a model that classifies patient state based on some description from a given patient. So let's say that the patient sends input being heart pain. Then we embed the input, so we go from the words to some word embeddings. And then on the level of these word embeddings, which are basically the vector of parameters for each of the tokens, we also add additional embedding, which is soft prompt. It's additional parameters, vector of parameters that is added or so-called prepended before the embeddings for specific tokens. So just think about this soft prompt as additional parameters that we prepend to the other parameters in the embedding space of the model. So to obtain the canonical algorithm to train models with privacy, so to obtain DP-SGD for this soft prompt, we just don't train any model, we just train parameters for this soft prompt. And again, we just need these two additional red lines to be able to provide privacy. So here again the sigma determines the noise that we add to the clipped gradient, and the C, upper C, is the norm bound, which is for the clipping of the gradients. So this looks the same as for standard DP-SGD. We just changed from a given model to a soft prompt. So this is a very simple application of DP-SGD. And now, how do we incorporate DP-SGD into the training of the soft prompts? So we start from our initial parameters for soft prompts. We also have our private data with labels. So we provide the private example like the hard pane and the embedded. So this is this part. And the embeddings are, in this case, embeddings for the private data are appended to the parameters of the soft prompt. Once we have that, in the next step, we run this new input through the model, in this case being large language model, and then we compute loss as usual based on the labels for this private data. Once we have this loss, we compute the loss, we then can compute what are the gradients for the soft prompt. Then once we have the gradient for the soft prompt, we proceed in the standard way. We clip the gradients to specific norm, and then we also add Gaussian noise to the clipped gradients. So this creates privatized gradients. Once we have this gradient privatized, so we don't allow these gradients to express exactly what is private data, we can update with this privatized gradient the parameters of this soft prompt. Okay, so this is a very simple application of DP-SGD to the soft prompt for large language models. Now, how about PATE? To discuss PATE, we have to first explain what is the other way how to adapt LLMs to specific tasks, and then it is called in-context learning with discrete prompts. So here we have so-called prompt template or meta prompt. So in this case, we give instruction. For example, here we want to classify a given movie review as being positive or negative. And then we give some private demonstrations, also called shots. So we show, for example, that if the movie review was this film is a masterpiece, then the model should return answer positive. Here we have no backpropagation, no training of this meta prompt. We just select the best demonstrations. We also can tune the instruction to prepare the best prompt for this LLM. Once a new query comes, we want to classify this new my input. The movie was great. We want to classify what is the sentiment of this movie review. We append this new movie review, the movie was great, to this whole prompt template called also meta prompt, and this whole input is passed through the LLM. And the LLM, having this additional information, can infer that this movie review actually is also positive. The disjoint subsets from the private label data are used to create demonstrations for private teacher prompts. Data serves as private shots. And from teacher answers, we construct a histogram. Each teacher has a vote. In this case, if a movie review is positive or negative. To protect privacy, we add the Gaussian noise on top of the vote counts. Intuitively, we do not want any single data point from the teacher prompt to influence too much the output of the predictions. Thus, in these settings, the random noise added to both vote counts prevents the outcome of aggregation from reflecting the vote of any individual teacher, and in this way, we protect privacy of the private data points. Finally, these privately labeled teacher examples are returned to prepare a so-called student prompt. So we choose labeled examples that give us the highest accuracy on the privately labeled public dataset. And here, note that in this case, we don't train a new model called student from scratch, but we prepare a new prompt, which is based on the labeled public examples. So with that, thank you for your attention. Today's lecture was based on these references, so please have a look if you are more interested in a specific topic or you would like to understand in depth a given concept. And then thank you for your attention.